Hello, this is the Unit 2 overview. I'm just here on the Patterns Approach website, and I'll just scroll down on the home page just to do the quick year level zoom. So Unit 2 comes after, obviously, Unit 1, where we established the 4 anchoring patterns. And so here we are in texting and driving, right here, second, seeing several of these. Really, we got proportional, horizontal line, quadratic, proportional, and even a negative linear in there as well. So I'm going to go to Unit 2 and now zoom in a little bit. So here we go. Unit 2 is going to focus on the performance expectation, design a solution to a complex real-world problem by breaking it down into smaller, more manageable problems that can be solved through engineering. So several assessment opportunities that I'll take a deeper dive. And then here, let's talk about the storyline. So this storyline comes from, if you can get buy-in from the health teacher, that they want to have some data around texting and driving. So often texting and driving is kind of a shock and awe, scary commercial. So we want to have some numbers around that. So our essential question is, how do we use STEM to enhance a social discussion? It culminates with them arguing from evidence around using the evidence that they cite is a simulation that they program. Actually, so that would take us back to the computational thinking, and they actually get the equations that they program into that simulation from experiments that they do. All right, so let's then hop to, so they get that hook right at the beginning, and then just like a physics teacher's dream, we want to teach them that when you have a difficult problem, you got to draw that picture. You got to think about what you know. What do you need to know? What do you need to learn? And actually, this is more sophisticated than just like a back of the chapter problem. So we really got to take that deep dive into system analysis. I think all the cross-cutting concepts, systems and system modeling. And then we might even, or we will realize that there are some models or physics equations that we need. So we need to do an experiment so we can construct those. And then again, put it all together, code our app, which is a simulation, a very simple one. It has no like VR goggles or anything, but a simulation of texting and driving, and then use that simulation as evidence in our arguing around using STEM to enhance a social discussion. So you can see the rest of the page obviously on the page. So I'll just do a quick scroll down to show that, again, each task has a task narrative that gives you some more details, and then a slide deck right here that gives you minute by minute. And there is a lot of tutorials, video tutorials, levels of support, and we'll get into that right now. All right, so again, just always going to start with this arrow as we go through a lot of information in this video. All right, so launching it. So we have a warm-up question always, just think CAT CER or, real simple exposure to breaking down a complex problem. So here, we just start with ordering a pizza, and it doesn't need to be a pizza, whatever resonates with your students. But, just ordering something, and what does it take to make that food? Then here I wanted to show this full slide because if you do have a health teacher that's willing to play along, and here's a sample email down here in the notes, if you can get them to email, overwhelmingly, health teachers are glad to get involved with this, and they almost always talk about texting and driving somewhere in their high school courses. So that's just a real authentic need, and it can be really integrated into what they do in health class. So we now have students that come back and say, oh, we're using the simulation we made in 9th grade. So that's pretty cool. All right, so as always with the engineering problem, we want to get clear on what we're going to do. And we have that sentence stem, nothing amazing, but it's really nice. They put it right on the front of the packet, that engineering problem statement. So we as physics students are making an app, customizable app for our health class students so that they can get numbers to texting and driving. And then every day we start with that. And of course, we also are filling out the storyline as we progress. Students are hand drawing that in, but boom, every day it's right there and clear. Okay, I wanted to also show that we have, 5 videos. So there's the long one that kind of has all the story. It's good to watch the first time, but that's pretty long to rewatch. So you can go to the short after that, just 30 seconds, watching that multiple times at the beginning. So we start priming our brain with what's going on with texting and driving. And then there's a very suggestive one, or after you've made it and they've come up with all of the things they need to really key in on, we can go and show the short with graphics. Excellent. So wanted to show that we were up here with the problem statement. Then we are going to start brainstorming. And we have just found that it's so useful to maybe start with whiteboards. And so it's kind of messy hand drawing, and then really start to emphasize that in engineering, you got to organize information, thinking about it. So that's sort of our rough draft of our system analysis. And then I want to give a peek at the final system analysis. But before I do, I'll just say, start simple and build the complexity. They're going to come up with all sorts of ideas. Oh, if it's nighttime and how drowsy you are, that's awesome. We love that, but we want to start simple and build the complexity. So here is a peek at the answer key, which is again in the packet. So after they do you want to get something close to that, maybe even start getting them to go vertical. And then we bring the good stuff that each group is doing, and we have a system analysis here. So that makes that polished one. And actually, on the fly, I'm deciding I'm going to hop up to here and just show, here's the final one. So you can just see the value that if we set up the system analysis on day one so that it helps them, they don't have that first spreadsheet coding, just goes a lot smoother, and students are like, I can do this. So that's what we want. We want to build their STEM identity. So let's set them up for success. So here is some pretty close to this, and we've made a lot of support videos. So you want something pretty close to this, and it's going to ultimately come down to actually, it's really nice. I didn't say this with the pizza, but with the pizza, we end up, how do we break that down? Make it, bake it, take it. And then with texting and driving, distraction, reaction, traction. People like rhymes, but distraction, reaction, braking is also fine. So the total distance is going to be obviously how far the car goes during distraction, reaction, and braking. And then ultimately, it comes down to just comparing how far was the walker compared to how far the car is going. And it's a nice little touch. Here's an if statement. So that's sort of a bonus, and it's a nice one. And it kind of makes sense that, hey, if the distance the car goes is bigger than the walker, hey, let's quote them, call 911. And of course, if you output a text from an if statement, you need to put quotes. But it also kind of makes sense to students when you're doing this on day one. This one, they need guidance. They're just going to be really listening to the teacher on this one. I'm going to quote you, call 911. What would you say if, the car stopped short of the walker? Hey, I'm going to quote you, you need to be more careful. So good stuff there. It's pretty fun. And that's something that almost no student has done before. All right. So that is our overview of the system analysis. And then we're about to move into the need for finding models. And let me just go back and peek. So where we had the velocity of the car, we got that from the video. Time of distraction, hey, we got to do a mini experiment. And time of reaction, a mini experiment. So let's go and do that. And, it's just something real simple, like left half of the class, you figure out distraction, right half, reaction. And we want this as open-ended as possible. It's fun. They pull up video games, driving video games, and try to like text at the same time. But if you want structure and it's the first time, we do actually have a little bit of structure, and you can go down and there's some resources. There's various driving games that they can play, and even some apps that do a reaction time test. So those are there for you, but minimum help for students to be successful. They, need help with designing, right? So later in the course, we really want them to get good at that. So exposure, practice, mastery. All right. So you can see, then we would fill in the time of distraction. And of course, that's customizable. That's a green input. So it's very changeable, but we want to have a common one so we can check our coding. And we already know from unit 1, velocity times time gives us the distance the car goes. So we're actually all the way down to the velocity of the car before braking. Here, I will just point out that we're about to go and find out the distance while braking, but here's a time we really want them to understand the system analysis, and we don't get to do stronger and clearer too often. It's a big lift, but students almost always feel so good after it. So this is one of those things that we got to give them time to get competent with it, and stronger, clearer is that time. So, A will say it to B, and then they get complimented, and then B says it to A and they get complimented, and then you rotate 2 or 3 people, one person to keep it simple, 2 or 3 people, so they're kind of not sure exactly who they're going to get or try to line up with their friends. All good stuff there. But in any case, they do that 3 times and they kind of groan. But almost every student, and even in the summer workshops, teachers go into it like, oh man, almost everyone feels good at the end of this. There is this like, they got better. They really understand that system analysis, and then it can do its job. It can guide the learning. Students then say, hey, what else do we need to do? Oh, we need to figure out the deceleration due to braking. And of course, what haven't we done in our swirl yet? Speak, write, interact, read, and listen. They've done a lot of this with those mini experiments and the brainstorming, but we haven't done a lot of technical reading. So you guessed it, we have a technical reading, and it's not that technical, but in any case, it does have words and essentially a graph or diagram here. And this is taken from the Oregon Driver's Manual. So real text relevant to students' lives. All right, so then we would have the deceleration due to braking, and our system analysis guides us. What do we need to do next? Oh, we got to figure out the time of braking. All right, so again, we're kind of wrapping up the models, and we're going to even start using computational thinking to do that. So there's a few different ways you can do it, but if you kind of just think about it, if you're going 20 miles an hour and you slow down by 5 each second, okay, 15, 10, 5, 0. Most students can just kind of figure that out, but we want them to, play with it, build some graph literacy. So, hey, as you increase your time, no surprise that the time of braking is going to increase. Hey, if you increase the power of the brakes, it's going to slow down quicker, and no surprise. So they get to play with that. And then really, it's in a sense, a multiple choice. So they get through that exploration, computational thinking, graph literacy, they figure out the time of braking. And you guessed it, we go and put in our system analysis. And then what do we do next? Students should be able to figure it out. We got to figure out the distance the car goes while braking. So again, start simple, build the complexity. Hopefully you're seeing that come up again and again. And here the start simple is a moving car that's decelerating, that's complex. So what's the simplest acceleration? Speeding up from rest. So let's do that. So we're going to do an investigation to determine the mathematical model for constant acceleration, the simplest constant acceleration. So we're going to roll a ball down a ramp, just classic physics. All right, but the thing I want to point out here is that they really can hypothesize quadratic. They know that distance and time for constant velocity is proportional. They also, especially if you review it, will remember that the rate of change or slope of that line is the velocity. And if it's speeding up, we've done that. If you have those posters on the wall, they know it's one of those 4 posters. They know it's not horizontal line. They can kind of eliminate proportional at this point because that's constant velocity. And they know it's not inversely proportional. So nothing primes their brain for success like hypothesizing and reasoning that it's going to be quadratic. And they might need a little guidance, but want to point out that we can guide them to cue that information up without telling them the answer. And I'll just say that is such a STEM identity builder that they kind of reason. They're not sure though. I mean, don't get me wrong. They're not sure. All right. And then if you just take a peek, I'm not going to open it, but the data table is exactly the same as we had for Unit 1. So that's really nice. They can video it, and they get good data. Works out really well. So what I want to show though is, again, there's that card sort, and this is even mixed up on the card just in case students see it uncut up, but you'd cut them all up, mix them up, and they get it that, yeah, no surprise that the steeper ramp has the steeper curve. So what is that number? Well, they might say it's the ramp, but the big pivot there is We took data on the ball. What does a ball have because it's on a steep ramp? Oh, it's fast. Well, actually, all of them eventually get fast. So it's not fast is a good idea, but oh, it's how quickly it gets fast or the rate that it changes its velocity. And of course, that is acceleration. All right, so I just also wanted to show after they do the card sort, that's right here. This is the bottom of the graphic organizer. They walk the triangle. And of course, there is that 1/2 in there. And you can see the notes. But the quick answer, I think for a lot of us, I've been now convinced through just so many discussions with teachers, is save this for junior, senior physics. Really spending the extra day to get them to construct that it's 1/2 the acceleration. You want that day back when we are talking climate change and electric guitars. So, just saves, the advice is save something for junior, senior physics. And then you can just see the end of the graphic organizer ends up really helping them, direct them to be successful with the conclusion. And that's the last one that's going to be like that. So unit 1, 2, a lot of support, a lot of guidance on writing a high school level conclusion. And with these, now we're ready to start moving that away. But of course, those supports are always there and can be selectively given, minimum help for students to be successful. So different classrooms are going to be at different points, and different students within each classroom will be at different points. But those are resources there for you. All right, and then to just summarize it, at the end, we get the simple equation for acceleration, and through an activity, they put it together that, hey, if you're on a constant velocity bus and you roll a ball down a ramp, hey, it's going to have the distance the bus moved, velocity times time, plus how much it moves on the ramp, 1/2 acceleration times time squared. And again, beautiful thing. Why is it quadratic? They know this now. Hey, if you double the time, yes, it has twice the time to move forward. And if it's accelerating, it would have twice the time to speed up. So the contribution of acceleration is going to be 1/2 acceleration times time times time. That's a little bit funny with the word time, so I'll just say it one more time. 1/2 acceleration multiplied by time multiplied by time. So we expect 2 times in there because one is allowing the ball to roll longer time, and the other one time is in there because it's speeding up the ball. All right, so we're back here. We get all of our equations in. We're all set. And I already gave that peek. So I'm just going to jump over and look, they are going to code. And again, there's 3 levels of support. I'm about to show that, but I just want to say, ideally, it's really nice if they start with a blank page. They make this drawing on the side. They make everything. There's a video support that walks them all through. But due to time or just the right appropriate challenge for your students, you might want to look at level 1, level 2, or level 3 support for coding the spreadsheet. And they each have their customized video tutorials. So think about what is the right level for your classroom. All right, so with all of that, they're in there, they got everything in. And we've said start simple. Remember at the beginning, we talked about, hey, if you're sleepy or tired, okay, let's circle back. We can now do that. So here's a student-made video. We'll just quick watch it, but you could take on sleepy. What are you going to do? You're going to add time of distraction. But here, or if the roads are icy, oh, that's going to affect the time of the tires. So we'll just watch this student-made video. Okay, so that's that shock and awe that we kind of have come to expect. All right, so they drifted into oncoming traffic. I'll just quick show this. We got to change. It's no longer the velocity of the car. It's velocity of the car approaching truck. And we, of course, talked about relative velocity, not in this video, but I'm going to go down and change it in all 3. We want to, obviously tell them to change it, and we might even highlight that change. And then, so if the car was going 10 and the truck was going 10, they're approaching each other at 20. And I want you to look down here. Yep, it changes it everywhere and everything. That's the power of computational thinking. So we can now quickly take on a car drifting in traffic. Oh, you're tired? Okay, reaction time while sleepy. All right, this is the power of reaction time goes up to 1 second. Recalculates. Okay, this is the power of computational thinking and starting simple. And now we can take on very complex situations quickly, get some real numbers to start thinking about this, enhance a social discussion with STEM. All right, so with that, we wrapped up computational thinking, and it's time for us to make our argument from evidence. And what is so cool, I've said it before, but I just want to say it one more time, is that their evidence is a simulation, very simple, straightforward simulation. And it could be that other screenshot here, but we encourage students to mix it up and make it their own. And this is actually from a student before we had them make those pictures. But in any case, their screenshots are of a simulation that they programmed from data or from the pattern they found in data of an experiment they performed. So that is pretty awesome and something to celebrate with students. And of course, writing, most students are not excited about, but they're a little bit more willing because of the nature of, in language arts and social studies, they're always referencing other sources. Here, they're referencing a simulation they made. So here, I'm just looking at the key. So lots of good stuff. And then, of course, it's always nice for them to come up with a new situation. This one wanted to look at a drunk, distracted driver and make an argument from evidence. And then we end on reflects on the impact of science on society. So really cool that they really do see how they're using science and engineering for a social discussion. And it's something we always hope for with students, but so often don't really ask them to write about it or explore it. So there's an opportunity built in to that assessment. And then, writing, always tough. So we want to, again, support them to be successful. So just want to call out, there's a lot of supports. And some students are going to be ready before others. So here is some extensions. They all like modifying, that simulation was in meters per second. Of course, lots of students are thinking in miles per hour. So build in that converter. And that gives, though some students are extending their learning, and that's freeing you up to spend some more time that need more teacher attention on the CER. Okay, and just wrapping up here, just want to call out that this is so rich opportunity to talk about cross-cutting concepts. Obviously patterns, that's so easy. Cause and effect with what's going on. Structure and function around cars and cell phones and apps and all these good stuff. System models we talked about. Energy flow, you can really talk about where's that energy going, and brakes take large scale kinetic translational motion energy, turn it into thermal or regenerative braking. All good stuff, because our next unit is around energy, so you can talk about that. Scale, proportion, and quantity. You can really look at the scale of what's happening during the distraction, reaction, and braking phase. And you'll notice one really dominates. The scale of it turns out to be really important. All right. With that, that is the full overview. There is a shorter one too, if that's the right fit for you or a colleague. With that, always appreciate feedback.